We are now ready to learn about compositions of linear transformations. The example that I'm about to do is like problems 39 and 43 in your homework. Theorem 611 in your book states that if you have two linear transformations T1 and T2 with matrices representing them A1 and A2, then you can apply the two linear transformations sequentially to a vector v, and so we need some notation. T2 composed with T1 is also denoted as T2 of T1, indicating that function T1 is applied first and T2 is applied second. That the composition of two linear transformations is itself a linear transformation, and the matrix that represents the composition of linear transformations is simply the multiplication of matrix A2 and A1, representing transformation 2 and transformation 1. So for section 6.3, your Desmos activity will be at R2W A2E, the student.desmos.com. So you can go there and complete the activity anytime you're ready. I do recommend watching this video, as you might obtain some good answers for it. So let's see. Let's suppose we have a transformation given by the reflection in the y-axis of a vector. So we flip about the y-axis. And another transformation representing counterclockwise rotation by 45 degrees. Then what we want is to find the matrix, the standard matrix for the composition T2 with T1, and the standard matrix for the backward composition T1 with T2. So we find that, and after that we find the image of the vector 1, 1. We kind of know where it lands, but we'll see exactly how these matrix multiplications help. So to find the standard matrix for the reflection in the y-axis transformation, we want to put vector I, 1, 0 through the transformation, and vector J, 0, 1, we put that through the transformation as well. So we make x equals 0, y equals 1. Now, these vectors will become the columns of the standard matrix A, A1 rather, that corresponds with T1. Now, in the previous video, we saw that there's we were given a general matrix, so this is worth remembering, or making a note of it for the purpose of the test. T2 is going to be given by so counterclockwise rotation by 45 degrees, or by pi over 4, will be given by cosine of pi over 4, negative sine pi over 4, sine pi over 4, and cosine pi over 4. So I picked this because the numbers are easy to work with. Now, if you are, you notice that there's a common factor in all 4 entries there, what you can do is you can pull that factor out, and the resulting matrix, let's call it A2, and this was A1, this is matrix A2 together with the constant in front. It's easier to work with. So it's harder to multiply things that have radicals and fractions in them, but if you just have ones and negative ones, it's easier to work with. So now, I am going to try to find the matrix that results from composing T2 with T1, or T1 with T2. So in order to do that, we want to multiply the matrices, the standard matrices for the two transformations, T1 and T2, in this exact order. So if you're going to apply A1 first to V, that means T1 goes on the inside of the transformation. So then the A2 transformation is given as above here. And so this here is A2 times A1. This is a reflection in the y-axis. This is rotation by 45 degrees. So if we multiply them, this is the composite linear transformation that lands you at the end of both motions. Right? So you do these two actions, T1 and T2, and this matrix will help you cut to the end, so to speak. So let's see. Next, let's try to find the transformation that results in composing T1 with T2 in the reverse order. So now, first, we do rotation of 45 degrees, and then we reflect on the y-axis. So if we're to do that, this is the A2 matrix, and I put the constant out front because, all right, this needs a circle. The constant is going to be on the outside because you're allowed to move the constants anywhere there. So then we just end up multiplying these two matrices, and this is the matrix that we get. So now let's see what happens as we put our vector 1, 1, and we try to find its image through the composite transformation. So it is enough to multiply it by the product of the two. And then we see that it lands at, so let's see, negative 1, so that's negative 2. And there's a constant out front, and then here, this is positive. Negative 1 plus 1 is 0. So if you distribute this inside, the 2's cancel, so you just end up with negative square root of 2. So let's see exactly what happened to our vector. We had, initially, we started with the vector 1, 1. What T1 did to it is it reflected it in the y-axis. That means anything that was positive here will end up being negative, and the y values stay the same. So this here was a reflection in the y-axis. So, if you use common sense and you do this reflection, you will land at negative 1, 1, which is exactly what we saw the transformation do. Next, we want a rotation. So that was the first transformation. Next, we want a rotation of 45 degrees. Now, we know that this here is what 45 degrees is, right? So negative 1, 1 is right in the middle of the second octant. So effectively, by rotating this vector 45 degrees, you will land somewhere past 1. You will land at negative square root of 2 on the x-axis pointing this way, right? So this is this vector here, negative square root of 2, 0. Now, what happens if we try and maybe take this vector and we put it back through the inverse composition? So we want to see what happens if you do this in reverse order. So I finished with what I was going to do. Now I'm just playing around with this. Let's see, what would be the inverse transformation of the vector negative square root of 2, 0? Well, that means we're going to take the inverse transformation as we computed it here, square root of 2 over 2, and negative 1, 1, 1, 1. Let's see if it works. And we're going to multiply it by negative square root of 2, 0. I'm going to keep this guy out here, square root of 2 over 2. And let's see, this is negative square root of 2 plus 0. So that's negative square root of 2. Oh, wait, no, positive. Negative times negative is a positive. And then negative square root of 2 plus 0. So now if we distribute this inside, we will end up with, let's see, square root of 2 times square root of 2 is 2 over 2 is 1. and here we end up with -1. So effectively, we took this and we ended up with 1, -1. So we applied the same transformation. So now we applied reflection on so x and -1. So we landed here. So what this transformation did is we reflected it, and then we so it seems like it's reflection on the y-axis and then clockwise rotation. I might have lost a negative. I'm going to quit while I'm ahead here. This is supposed to have gotten us back to where we started. And I'm going to work out the kinks. This is my 3rd time recording the video, so I hope that's okay. So don't forget, that is your activity for 6.3.